In this example, we are going to deal with independent events. A fair coin is thrown twice. Find the probability of getting tails on the second throw, given that the first throw showed tails. Well, we are dealing with independent trials here. So you probably know that the answer is a half. The probability of getting tails on the second throw is not affected by how the first throw turned out. Whether the first throw was heads or tails, it has no effect on the second throw. But I just want to discuss independent events in connection with conditional probability by using this very simple example. I want to let A be the event of getting tails on the first throw and B be the event of getting tails on the second throw. Here's the sample space for the outcomes of two throws of a fair coin. We can see that we have 4 equally likely outcomes. So event A consists of these two outcomes. We have tails in the first throw. B consists of the outcomes which have tails for the second throw. So here we want the probability of B given A. The probability of getting tails on the second throw given that the event tails on the first throw has already occurred. Well, we can apply the formula, or we can just refer to the Venn diagram. So we're selecting from A. So we're just selecting from this set. So we need to find the outcomes in A that belong to B. Well, we see that there is only one outcome. So when we take a random selection from A, there are 2 equally likely outcomes, and one of them is part of event B. It belongs to B. So we can easily see that this answer is a half. But that's no surprise. The probability of throwing tails is a half, regardless of what the first throw. Let's just apply the formula. What's the probability of A intersecting B? Well, to calculate that probability, we count the number of elements that are in both A and B. Well, there's only one element in both events. And we put that over the number of elements in the sample space, which is 4. And then we divide by the probability of A. So on top we have the probability of B intersecting A, and underneath we divide by the probability of the event that's conditioned on. We're conditioning on A, so A has to appear in the denominator. So we're reversing the letters in this formula up here. The probability of A is a half. There are 2 elements in A, so it's 2 over 4, which is a half. A quarter divided by a half is the same as a quarter multiplied by 2, which is a half. Now, since A and B are independent events, we know from a previous video that the probability of the intersection of these 2 events is just got by multiplying the probabilities together. So let's look at our conditional probability formula. We can replace the probability of B intersecting A with probability of B times probability of A. And if we divide by the probability of A, you see that we get the probability of B. This is no surprise because B and A are independent events. The probability of B given A is just the probability of B. So conditioning on A does not change the probability of B. Now suppose we turn this around and consider the probability of A given B. Well, that's the probability of A intersecting B divided by the probability of the event that's conditioned on, which is B. Well, the probability of A intersecting B is the probability of A multiplied by the probability of B, since A and B are independent events. And we divide by the probability of B, these cancel, and we get the probability of A. So in summary, if A and B are independent events, then the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B.